What I would like to do, first of all, let me introduce where I'm coming from. So I'm part of the Bartlett at UCL. I'm a professor and I'm leading there the Smart Buildings group. And what we're looking at is looking and focusing very much on operation and information management workflows. So what I will be talking is about ontologies and knowledge graphs and everything that we have been talking in this first session. But I will be focusing slightly more on buildings and buildings operation. So very much the interest of what I'll be presenting is this, and in particular, we'll be asking the question of how we can make data access and the benefits of the digitalization something that can be applied horizontally across the building stock. So in terms of the work, this is the work that has been done with my group, and it is linked to two relatively large European projects. And I will be using, because I didn't know what the audience was, the context of a case study that we're doing. It is one of multiple buildings that we're working with, and I'll be focusing on one of the buildings at UCL East, which is the new campus of UCL. So I'll be showing some images and some stuff linked to those buildings, just as a way of helping you have like a more concrete idea of the complexities associated with dealing with the real world. Now, in terms of giving you some sort of image, I mean, the use of buildings and building twins is something that has been investigated for a long time. And the main challenge is one of complexity. So no building is the same. So these are two buildings that are new UCL buildings of the UCL estate. One Pool Street West is the one that I'm going to be focusing on in this presentation. But the main idea is that they look very different, they're structured very different, and they're very typical in that each building that we see and we know in the built environment tends to have a difference. So what is a building comprising in? I mean, there are many different perspectives. There is the architectural element, there is the lighting element, there's the BMS element, and there's the heating and cooling system element, just being some different, if you like, perspectives. And for example, this building, looking at Pool Street West or Marsgate, they have thousands of data points coming from the different systems meant to be using and supporting heating and cooling, and in general building operation. Now, the biggest challenge is the following, that UCL or an owner would pay quite a lot of money to get these buildings in place. So this was many hundreds of millions of pounds spent for those two buildings. But when it comes to operating them, this operation tends to be very inefficient and ineffective. So the question is how we can identify such inefficiencies and possibly drive action to improve them. So the second challenge, and I think that is the interesting one, is that while we know how to do that and while we can identify and go and do the triage process in each building individually, the problem is one of complexity and scaling up. And unlike other domains, like the automotive industry, where we have a car like a Tesla and we're producing it millions of times, in the case of the buildings industry, each building is different. And so we need to be able to develop structures and infrastructures that allow us to write code and generate applications that would allow us to do that in a very transparent way. So we need the separation, if you like, from the building to the application layer. Now, the way we do that and the way we approach that is something that we haven't been successful so far in the building industry. All these integration tasks happen manually or semi-manually. And the problem is that these tasks happen late in the delivery process, and that lateness introduces a lot of time pressures, and usually this work doesn't happen very well. So while we can create monitoring systems that can identify inefficiencies, or we can improve the operational aspects and operational parameters like control, in many cases, this becomes an afterthought and it is very late, and we have buildings going on for years. And the impact can be increased bills, it can be reduced comfort, it can be all this together. For example, in the case of UCL East, maybe UCL is paying 100 or 120,000 pounds more than they could have just to get that basic quality of service that the building was designed. So the challenge is how we can do that and how we can do that horizontally. And so the main aspect that we have been concerned about is how we can do that in a portable way. And how we can develop applications that can be developed once and deployed multiple times. Now, the problem when we start looking into the details is that, as I mentioned, each building is different, not only from a geometrical context, but from the way data are coming from. And we have a custom system design that will change from one case to the other. And therefore, what happens is we have different information and data coming from different data points. And that information might be isolated from one to the other, and the context might not be easy to cross-reference. And in general, it becomes very hard to go from having access to the data to cross-linking, cross-referencing, normalizing the data, and getting access to insights, which is what creates value in the process. And I don't probably need to pitch that to this audience, but one of the issues that are quite important is having a shared understanding and this lack of interoperability, or if you like, the multiple perspectives is one of the reasons why we cannot facilitate and streamline that process. This is one example, which is contextualized to application. This is how a naming convention of a system comes from the BMS system. And what we can look here is that this relates to an air handling unit, to a specific zone ID, and then it gives us the temperature set point. So what it says is that we have all these naming conventions that are specified at each project level, but then these tend to be very ad hoc and not easy to read. So the idea is that we can make things more transparent and we can accelerate that. So the idea is that in a traditional workflow, we go to a building if it's existent, or we look at what are the data points, we develop the application. This can be deployed on some embedded device or embedded computer. And then we do a configuration and we run this application, and this tends to be a very static process. I mean, studies can highlight what is the cost of this. In general, this is not a very transparent and easy to do process, especially if doing it afterwards, because there is a lot of issues associated with documentation. And this can cost several hundreds of dollars per point, and this is just one indication. But also that manual bit, which comes afterwards, tends to be done again and again and again, and this doesn't represent value add, but rather it represents an iterative process that is not the best use of the time. So not only our group, but there has been a lot of discussion about how to develop and work on standardized metadata formats. So there was a discussion about semantic web technologies. There was a discussion about knowledge graphs, ontologies, and this is exactly what we are working on. And we're looking at how we can develop and deliver application portability using a semantic knowledge graph interface. So I'm not going to go into the details because I think this have been covered already. So we're using and we're selecting certain ontologies. In this particular context, there are quite a lot of application ontologies that have been used for quite some time. There is a report that we created in the context of Annex 81 about the different data models for buildings. And I think there was a mention before about BOT. There was a comment about SAREF. These are relevantly interesting buildings. We're using quite a lot Brick and ASREI 223P, which is a standard which is emerging in this context. Now, the idea is that we link and cross-reference the conceptual layer with data that we're capturing from the domain, and then we can separate through an API which is very clear and horizontally the same across buildings, the applications. We can do queries around the knowledge graph and then deploy functionalities around different buildings. And basically, we have been looking into testing that in the context of different types of services. And these services can be services related to control, to monitoring, to benchmarking, to forecasting, and so on. So here's one example of how that works. And the main idea of this is as we go from design to operation, we develop data and artifacts. And I'm not talking about the data that are captured during the actual operation, which is, let's say, data from sensors and IoT devices, which come later into the stage. But I'm also talking about building information models in Revit or IFC, naming conventions, BMS documentation, structured and unstructured document. All these are potentially interesting data sources representing how the building has been developed and is organized. So what we're doing is we're looking at how we can harness all that information, which might be contradicting, conflicting, and uncertain, and how we can put that under one unified, if you like, data model. We're not looking at generating, even though we have worked on developing ontologies, we're looking at reusing existing ontologies where this is possible. And we're using quite a lot brick and real estate core in our particular use case. And some of the work that the link building data working group has been doing, which is the bot ontology and the web of things. So standards-based ontologies, most of the cases. And then we create an ontology network. So this is an ontology or ontologies that, or knowledge graphs that get aligned. And we can create queries so that we can configure and deploy the services. Now, within one of these projects that I was referring to, we were looking at how we can do this. And we developed an ontology that was specific because we had domains like district heating or electrical vehicle charging, which is not covered by some of these ontologies. But I think the main point is that as long as we select a representation of the knowledge domain that we're interested in, we can have some sort of compact and unified representation. In our case, the use of IFC or IFCR that was mentioned is a useful input because it does represent the geometric context. But in many cases, that geometric input is not so relevant in O&M context, and therefore we tend to simplify that, even though we use it obviously for visualization purposes. So here's the main idea and kind of what we have been working as a general pipeline, that we have different data that can be coming from different phases and different stages. They can be structured or unstructured. So this includes heating and cooling system data, the beam model, Kobe drops or other structured data. And then we can take part of this data and run ETL tools. ETL means extract, transform, and load, and generate partial graphs that then we can combine into a unified knowledge graph. Just to show how that works in the context of the UCL building that I was referring to before, we got as part of the design and handover of operation the beam models that were generated. These were very, very, very detailed, and our work looks at how we can take some of that information and infer useful aspects, and I'll explain what that is. This is only one bit. There is the documentation that came as part of the handover and the O&M manuals and all the plans. It is PME, which is UCL Energy Monitoring System, and other information that are coming from different locations. So what we were looking is how we can generate that knowledge graph and how we can automate that process. And when working with real data, the biggest problem is that this tends to be working with models that have a lot of noise. So standard model quality cannot and should not be assumed. So we've been working into algorithms, and I'm not going to go into the detail, but kind of say what the input and the output is, and can look at the detail into extracting information out of those files. For example, here's one example where we can take and process the architectural part of the IFC model, and then extract from that energy transfer surfaces for the whole building, which can be used to set up energy models, or infer the topological information and space and adjacency, which is important for energy flows, but it is also important for O&M context and facility management contexts. Another example, and this kind of goes into some more technical details, is looking at the MEP aspect and the connectivity of the different flow networks, and then developing tools that can automate that parsing and using geometric and other tools that we have been developing, generate aspects related to the HVAC topology of the building, so connectivity between different systems like air handling units and zones. And this represents another part of the graph and another representation about this specific building. So working along different domains, one can generate graphs or parts of graphs that are describing aspects of the system. For example, this is the energy metering architecture. And then all of this can be put together and cross-reference to the actual data that are coming. So a second part of our platform and our work is around accessing the data. And then what we can do is we can have an interface that looks like this, that doesn't, on the back end, understand anything about the building. It's only fed with a knowledge graph data. And then we can use that to explore or to run applications. In the interest of time, I'm going to skip a video of the platform or a demo of the platform. But what I would like to say is that everything hinges upon having on the back end that knowledge graph that gets generated and upgraded dynamically using the information that we provide. And then the second part is being connecting to the data stream, the 4,000 data points in this particular case, and being able to store and access that information. So once we have this information and all this infrastructure in place, we can start running applications. To ensure that a specific application applies to that specific building, we do and we run and we provide the information requirements in an encoded form. And we use this approach based on the SAPE constrained language to test if specific requirements are being met. For example, here, this shows the case where we have a point, and the point should be linked to a specific time series reference so that we have historical data about, let's say, a temperature set point or a temperature in a zone. And basically, our system is able to have small agents that can test all these requirements. And then if some of these requirements apply, for example, in this particular case, then we can deploy an application as an individual agent to monitor the system. And so what we can do is we can then start running applications. So in the interest of time, I'll just give you some examples. For example, in this particular case, this is a slightly different building. We could do control and we could dynamically alter the operation so that we can respond to signals from the grid. So this is demand response control, and we've been testing that. Or what we're doing at UCL is we're looking into monitoring, and we're looking at ideas like what has been described before, using, I think it was mentioned, GraphRag, and testing different approaches to use that knowledge graph as a way of providing some additional context so that we can create more natural language interfaces, but also embed within our knowledge graph some of the analysis that happens by our applications, like estimating set points, calculating overheating, understanding inefficiencies, and so on. So to conclude, I think the main part of what I have been talking is that application portability is important. So the scale up is an important part. And knowledge graph have a very important role to play within that aspect. Now, what we find is that generating those knowledge graphs can be a tedious and long process. So if we can find and generate those knowledge graphs from available data, and this is the pipeline that we have been looking at quite a lot, for example, BIM-based data or other data, this is great. But what we find is that in the real world, data are not working so are not meeting quality requirements. And it is important to have robust and resilient data transformation pipelines that can work with imperfect data. The idea of, and maybe that is a technical aspect of having sufficient data for applications can be automated using the concept of semantic sufficiency based on cycle-based testing. And then once we have that, then we can develop and deliver transparently applications. And we have been testing within some of these projects, monitoring and forecasting applications in the context of the UCL East building. And we find quite a lot of inefficiencies or issues with how the building has been operated, set up graphical user interfaces like the one I've shown before, or do control, which we've been testing in other aspects. And I think the important bit there is that if we can separate or automate that process of analyzing the data and then just provide that information contextualized, this can be quite useful, because what has been shown and what has been seen is that there is a big gap between data to insights, and kind of bridging that gap is where some of these ideas can be potentially very useful. With that, I will finish. If you're interested in more details, and there's a lot of details, this was meant to be a high-level overview presentation. Feel free to look at the websites of those projects or contact any of us, including the people whose work I presented today. And thank you so much for the attention.